So this is a new section about frequency domain analysis. First lecture, we will talk about Fourier Theorem and the Bode plot. After that, we will discuss the small signal transfer function and the Laplace transform. So then we will discuss the AC analysis in LTspice. The last lecture, 14, is about Laplace transform in LTspice using voltage-dependent current source or voltage-dependent voltage source. Now let's begin lecture 11. It's about Fourier Theorem and the Bode plot. So this is the introduction of frequency domain analysis. So in previous lectures, we have been focusing on time domain analysis and the DC analysis. So now we will enter the AC analysis in frequency domain. So AC means alternative current signals, such as sine or cosine, at certain frequency and magnitude. When we talk about frequency domain analysis, so there are some keywords are interchangeable in most cases. The first one is frequency domain analysis. Second one is small signal analysis. The last one is AC analysis. So basically, they are talking about the same thing. So why AC analysis is important? Because it gives you a brand new dimension and great insights of the circuit. Oftentimes, we have frequency-dependent components in the circuit, such as inductors and capacitors. We have studied them before in our previous lectures. We know that impedance are dependent on frequency. For this reason, the system with L and C behaves differently when the input signals as excitation at different frequency. Therefore, frequency domain analysis tell you the system response and the dynamics to a stimulus. In this example, we will show you a real-world model of a capacitor, including the equivalent series resistor ESR, equivalent series inductance ESL, capacitor C, and leakage resistor Rleak. The total impedance of Z has three parts, including C and Rleak in parallel plus ESL impedance plus ESR. Since these three parts are in series, we can simplify this equation using magnitude asymptote. In other words, we only care about the largest part and ignore the others. That means the largest part will dominate in the total impedance Z. This is the frequency versus impedance of each component. Notice that usually the Rleak is pretty big, so that we can ignore and assume it's open. So the final Z will be just three parts in series. The impedance of C, the impedance of capacitor is 1 over SC, and it is reducing as frequency increases. On the right hand side, we have the impedance of L, which is S times L. At higher frequency, SL has a higher impedance. So that we have two magnitude asymptotes. The intersection is called the corner frequency or the resonant frequency F0 or F0. At F0, the resonant frequency, the impedance of ESL and C will cancel out each other, so that we only have ESR left at omega equals to omega 0 or at the corner frequency. In lower frequency below F0, it behaves like a capacitor and the impedance is 1 over SC. At higher frequency than F0, the impedance is simply SL. So at the corner frequency, the impedance becomes ESR because the capacitor and the inductor impedance are cancelled out by each other, and they have 180-degree difference from each other. So that the ESR determines the impedance at frequency F0, which introduces some peaking at the magnitude. Also, the R0 is called the characteristic impedance. So this is a pretty busy slide, but just want to show you that the capacitor model is totally dependent on the frequency. So this is the impedance of a 1000 picofarad O4O2 capacitor over a wide range of frequency. from 100K to 10 GHz. I copied it from the datasheet. Apparently, the impedance matches our model, and it has two asymptotes as we expected. So when the frequency is below 300 MHz, it behaves like an ideal capacitor. So when the frequency is below 300 MHz, the impedance is reducing as frequency increases. It means the impedance is 10 times smaller at every decade in the frequency. So the total impedance is capacitive. If the frequency is above 300 MHz, the frequency increases and the impedance increases as well. And this becomes inductive. The reason has been explained before, and at such a high frequency, the parasitic inductance ESL dominates the impedance. At 300 MHz, which is the corner frequency, the ESL and the capacitor are cancelled out by each other. Through this example, you will understand how important the frequency response is in the real world. So why sinusoidal signals? So Fourier Theorem said a periodic function in time domain can be expressed by the sum of a series of both sine and cosine functions. Therefore, we focus on sinusoidal functions. In this lecture, we will introduce the frequency response of a system. So this is a very simple example about Fourier Theorem, or sometimes called Fourier series, founded by French mathematician Jean Fourier. It says a periodic function can be regenerated by a series of sine and cosine components at different frequency. So by using an interactive tool as shown in the reference, I created an arbitrary waveform in one cycle. It is highly recommended to give it a try by yourself. So now we assume this is one cycle of a periodic function f of t. This waveform's frequency is called the base frequency or the fundamental frequency. Now if we click the button to automatically calculate base function coefficient, the Fourier series of the arbitrary waveform is found by basic functions in sine and cosine at different frequencies. Note that the frequencies are at integer multiplies of the base frequency. Also, the first row gives the coefficient at zero frequency, which is the DC term. By using the coefficient of sine and cosine at each frequency, we can recreate this arbitrary waveform and plot it in the time domain. So you may notice that these two waveforms look like each other, and the Fourier theorem works pretty well for us. In summary, Fourier theorems give us great insights about AC components at each frequency. This is something we cannot easily obtain in time domain. So this is the true reason we need AC analysis. In this example, we put sine signal into the same RC network in LTspice. The input frequencies are at 10 Hz, 100 Hz, and 1 kHz. We use the same RC network, but we have different frequencies as input. Since we have the capacitor in the system, this RC filter will behave differently at different frequency. So we know RC filter is a low-pass filter, which means it will pass the low-frequency signal to the output and attenuate the high-frequency signal. So if we run the time domain simulation, we can see that at 10 Hz, the input waveform in purple is very similar to the output signal in gray. But as frequency increases at 1 kHz, the output signal is further attenuated and the phase delay is increased up to -90 degrees. Now let's zoom in and see more detailed information. So we are interested in two parameters, magnitude and phase. We can see that at 10 Hz, the input and output have similar magnitude, although the output is a little bit smaller than input, and basically they are in phase. So there's almost no delay between these two signals. In the middle plot, 100 Hz, the magnitude in light blue is a little bit smaller than the input, and also the phase of the output is lagging the input because it has some phase delay. How can you tell the output is lagging or leading the input? Assume Jerry, a mouse, is the input waveform, and it reaches a peak about this time around 102.5 milliseconds. However, Tom, the cat, reaches its peak at 104 milliseconds. Later than Tom. It means that the Tom is always lagging Jerry in phase, and that's why he can never get Jerry. If we look at the 1 kHz input, we see that output has significantly reduced magnitude, and the output has almost 90-degree delay in phase, because one period has 360 degrees, and the output has peak at the moment of the input reaches 0 magnitude. So therefore, the delay is a quarter of a cycle, that is 90 degrees. So in summary, higher input frequency will have more attenuation and more phase lagging at output, and the phase lag is up to 90 degrees. As we have studied the magnitude and phase, we will introduce the Bode plot. In addition to 10 Hz, 100 Hz, and 1 kHz, we want to know the transfer function of V out over V in over the entire frequency. If we sweep at each single frequency, we are able to obtain two plots, magnitude and phase. Horizontal is frequency in Hz. The first y-axis is magnitude of V out over V in. The second y-axis is the phase difference between V out and V in. Since V out is lagging V in this case, the phase is negative. Generally, we have a linear time invariant system, LTI system, working at a certain operating point, or called DC bias. We inject the small signal into the system and measure the small signal at output as a response. So in this case, the system is linear time invariant. So we inject the small signal into the system and measure the small signal at output as a response. So by doing so over the entire frequency range, we can get the Bode plot. This is helpful to understand the AC dynamics of the system at a certain DC operating point. By the way, the Bode plot is created using the MATLAB. This is the code I use for the MATLAB. If you have MATLAB available, you are welcome to run it as an exercise. FFT, fast Fourier transform. So a fast Fourier transform is an algorithm that can sample a signal over a period of time and divide it into its frequency component. In this particular example, as an illustration, we have waveform plotted in time domain in red. Actually, it consists of 3 different frequency components. So by using the FFT, we can tell that there are 3 major frequency spikes at different frequency. This will be very helpful to understand the waveform better. So this example is a voltage divider, so we will use it to study the FFT. The input has 2 sine wave signals at 1 kHz and 100 kHz. Assume the 100 kHz is a high frequency noise. We want to filter it out by the RC filter. So far we will ignore the capacitor and focus on the voltage divider. If we run the simulation in transient domain, we can see that the input signal and output signal are plotted here. So if you just look at the waveform, you will notice that each signal has a low frequency component at 1 kHz and a very high frequency low magnitude noise on top of it at 100 kHz. So similarly, we can use FFT over this waveform to study it. If we go to View, FFT, and select the trace you want to study. In this case, it will be V of Vsen. So this is the output from FFT. Assume we don't know the input signal. So FFT tells us the magnitude of frequency components at a particular frequency. So we can see there one major spike at 1 kHz and a minor spike at 100 kHz as well. So other frequency spikes are because of the harmonics of 100 kHz. If we change the trace name to Vsen over Vin, we can get the FFT of the transfer function of a voltage divider. Basically, that's minus 20 dB over entire frequency, because that's the voltage sensing gain in decibel. Because the voltage sensing gain is 1 over 10, in decibel it is minus 20 dB. Because the voltage gain by the voltage divider is 1 over 10, in decibel it is minus 20 dB. We can assume this minus 20 dB over entire frequency and ignore the simulation errors shown here. That's all for this lecture. Thank you very much.